Alright, let's go. The Aral Sea that no longer exists. What you think of as a dying lake was once an inland ocean that could swallow entire armies and still have room. In the spring of 1948, a Soviet hydrological survey team anchored a flat-bottomed vessel somewhere near the center of the Aral Sea, in what is now the border region between Kazakhstan and Uzbekistan. The team leader, a geographer attached to the Tashkent Institute of Hydrology, lowered a weighted line over the side of the boat and watched it unspool past 20 meters, past 30, past 40, until the slack finally stopped at 68 meters below the surface. He wrote the number in a waterproof field notebook. Then he looked at the horizon, where the water met the sky in every direction with no land visible, and said nothing to the man beside him for a long time. Dr. Lev Berg, one of the Soviet Union's foremost ichthyologists and the author of the definitive taxonomy of Aral Sea fauna, had described the lake's basin in earlier publications as geologically ancient, a remnant of a much larger system that had once connected to both the Caspian and to even deeper inland seas tens of millions of years prior. When the survey team returned to shore, the depth readings were cross-referenced against Berg's earlier stratigraphic estimates. The numbers aligned in a way that made one of the junior researchers reach for a cigarette he didn't light. The basin's deepest prehistoric profile, reconstructed from sediment cores, extended past 300 meters in certain northern zones. The water the team had just crossed in an afternoon was not the Aral Sea. It was a shallow shelf above the real one. Soviet state press reported the survey as a routine hydrological inventory. The official summary noted water volume, salinity, and fish stock estimates. The stratigraphic appendix, which described the basin depth history and the Paleolake reconstruction, was filed separately and did not appear in the published version of the report. The prehistoric basin findings were formally incorporated into geological literature in 1957, classified under regional paleoclimate studies. The survey vessel's field notes were archived in Tashkent. A ministry official signed the transfer form. The press briefing on the broader Aral survey lasted 11 minutes and ended without questions from the floor. But the standard record of the Aral Sea's depth, the one used in mid-century development planning, the one that informed the irrigation diversion projects that would eventually drain it, never incorporated the full basin profile. And the discrepancy matters in a specific way. The prehistoric Aral at maximum depth held a volume of water equivalent to a column pressing down on you with enough force that every joint in your body would register the pressure before you reached the bottom. Not as a statistic, as a physical event your skeleton would remember. The salinity that rewrites biology. The ancient Aral Sea was not the lake anyone thinks it was, and what lived in it knew the difference. A paleontologist working for the Uzbek Academy of Sciences in the early 1970s was sorting through sediment cores pulled from a site near what had been the southeastern shore, her hands working through layers of compressed silt with a brush no wider than 2 fingers. She was cataloging foraminifera, microscopic shell-forming organisms whose shapes are locked to specific salinity ranges the way a key is locked to its cylinder. The ones she was finding in the deeper Pleistocene layers were not freshwater species. They were not even brackish water species. She set one sample under a portable field lens, adjusted the focus, and called across the tent to her colleague to come and look without explaining why. Dr. Zinaida Kuznetsova, a micropaleontologist affiliated with the Moscow State University Paleontological Laboratory, had published work on Caspian Basin foraminifera and recognized the shell morphology immediately. Species present in the deepest Aral cores were marine adjacent, consistent with salinity levels between 18 and 22 parts per thousand, nearly half the concentration of open ocean water, but multiples above anything the Aral Sea had registered in recorded history. Kuznetsova picked up the sample container and turned it over in her hand twice. She said the name of the species aloud, quietly, as if checking whether it sounded different outside her own head. It didn't change anything. The shells were what they were. The Academy of Sciences issued a bulletin summarizing the core findings as evidence of historical fluctuation in the Aral's hydrological cycle. Soviet scientific press covered the publication briefly, emphasizing the paleoclimate angle, the Aral as a record of regional water balance. The bulletin did not foreground the salinity readings in its abstract. A reader moving quickly would register the study as climate history and not linger on the organism data embedded in supplementary tables. The core findings were formally cited in a 1974 regional geology monograph. The sediment archive was transferred to the Institute of Geology in Tashkent. A signature appears on the transfer receipt dated November. The corridor where the boxes were shelved was reportedly flooded in a pipe failure 3 years later, though the extent of the damage to that specific collection was never separately assessed. And yet the salinity reconstruction holds in the underlying data. What it describes is a body of water that at its Pleistocene peak would have tasted like the sea on the back of your throat, salt enough to sting a cut on your hand, salt enough that your body, if you swallowed it for days, would begin drawing water from its own cells to compensate. The adaptation required to survive it long term would not be gradual, it would be total, and nothing alive in the modern Aral was built for it. The storms, the Aral Sea generated its own weather, and the weather it generated was not proportionate to its size. A meteorological officer stationed at the Aral's coastal weather post in the winter of 1952 was in the middle of a routine instrument calibration when the barometric pressure gauge began dropping faster than any seasonal front could explain. He tapped the glass twice with one knuckle, a habit, not a diagnostic, and then stepped outside to look at the horizon to the southwest. The water was still flat. The sky above it had a particular yellow-gray cast that he had not seen before in 3 winters at that posting. He went back inside and began writing in the observation log with the kind of steady handwriting that does not match what the face above it looks like. Dr. Vladimir Shapiro, a physical meteorologist with the Soviet Hydrometeorological Service, later analyzed the Aralsk station records in a 1961 study of inland sea storm generation. What the 1952 event represented in Shapiro's reconstruction was a self-generated convective system, a storm built not from regional atmospheric flow, but from the lake's own thermal mass interacting with cold continental air descending from the north. The Aral, at its full mid-century volume, was large enough to warm and destabilize the air above it in a way that created its own pressure gradient. The officer at Aralsk had watched a storm build from nothing in under 40 minutes. Shapiro underlined that figure twice in his working notes. Soviet meteorological reporting for the region described the 1952 event as a severe local storm associated with seasonal pressure differentials. The Hydrometeorological Service's internal bulletin, circulated among station chiefs, noted anomalous formation speed. The public weather summary for the Aral region that week listed wind and reduced visibility. The formation mechanism did not appear in the public summary. Shapiro's 1961 study was published in a specialist journal with a distribution of several hundred copies across Soviet scientific institutions. The study is cited in 4 subsequent papers between 1963 and 1970, all of them internally circulated within the Hydrometeorological Service. A librarian at the Tashkent Institute catalogued the journal volume in 1962. The spine of the volume in the archive photograph taken during a later inventory shows no visible crease from repeated opening. But Shapiro's data describes something the standard inland sea meteorology does not fully absorb. A lake capable of generating its own convective storm systems is not behaving like a lake. It is behaving like a coastal ocean in miniature, and the storms it builds do not require a seawall to announce themselves. They require water temperature and air mass and time, all of which the prehistoric Aral had in quantities that made the 1952 event look like a rehearsal. The kind of storm that comes from a basin 3 times deeper and twice as broad does not knock things over, it removes them. The creatures that adapted downward, the Aral Sea's endemic species, were not survivors, they were documents written in flesh about what the water used to be. A fisheries biologist from the Kazakh Research Institute of Fisheries was aboard a trawl vessel in the summer of 1963 when the net came up with something that didn't match the standard catch manifest. She moved to the sorting table on the deck, reached in with both hands, and held up a specimen of Aral barbel, a fish she had catalogued dozens of times, but this one had a gill structure visibly enlarged beyond any previously recorded measurement. She turned it once, set it down, picked it up again. The gills looked like they belonged to something that expected more oxygen debt than the current water column provided. Dr. Antonina Salnikova, ichthyologist and senior researcher at the Kazakh Institute, had spent the previous field season reviewing historical catch records going back to the 1920s, and had noted a consistent trend of respiratory organ enlargement across 3 endemic species over 4 decades. In the ship's small lab, she measured the gill surface area, entered it in the ledger, and then stood still for a moment looking at the number. She asked the vessel's captain without context how deep he thought the water was here. He said about 15 meters. She didn't respond to that. The Institute's annual fisheries report for 1963 described stable endemic populations and noted anatomical variation within normal parameters. The supplementary data tables, which Salnikova had prepared separately, listed the gill measurements alongside the historical series. The summary's language of normal parameters and the supplementary table's numerical trend did not point in the same direction, but they appeared in the same bound document. The report was submitted to the Ministry of Fisheries in Moscow. A ministerial review committee approved continued trawling quotas for the Aral the following spring. The supplementary tables were not referenced in the quota decision. Salnikova's field notes from the 1963 season are listed in the Institute's archive inventory, but marked as unlocated in the most recent catalog update. And yet the gill data, read across the full historical series, describes a population of fish spending generations compensating for something. The water they were living in was not the water their ancestors were built for. They were adapting downward, compressing their biology to fit a diminished environment, and the direction of that adaptation run backward in time points to an oxygen regime and a depth column that the modern Aral never had. To have needed lungs that large, their forebears swam in something that pressed on them from above like a hand on a shoulder, not gently. The sediment record, below the lakebed there is another lakebed and it has been waiting. A Soviet geological survey team working in the northern Aral Basin in 1966 was drilling a sediment core when the drill string dropped suddenly, as if the floor beneath the bit had opened. The driller pulled back on the controls and called the team geologist over without raising his voice. The geologist, a man named Petrov whose first name does not appear in the report, knelt beside the core barrel and looked at what had come up. The sediment changed color at a precise horizon, gray above, black below, with a thin orange band between them that smelled of sulfur when he broke it with his thumbnail. Dr. Georgy Friedman of the Geological Institute of the Soviet Academy of Sciences analyzed core samples from the northern Aral in a 1969 stratigraphic study and identified the orange horizon as an evaporite layer, a chemical precipitate left behind when a body of water evaporates rapidly, concentrating its salts before disappearing entirely. Below it, the black sediment was anoxic, formed in deep, still, oxygen-depleted water where nothing decomposed in the conventional sense. The material in that layer was older than the Aral Sea as recorded history understood it. Friedman wrote in his lab notebook that the sequence implied at least one complete desiccation cycle before the historical record begins. He underlined the word complete. The 1969 study was published in Lithology and Mineral Resources, a Soviet geological journal. The abstract described the stratigraphic sequence as evidence of quaternary paleoclimate variability. A review in a Moscow geology bulletin summarized it as confirmation of regional aridity cycles. Neither the abstract nor the review used the word desiccation. The word Friedman had underlined did not travel past the notebook. The core samples were transferred to the Geological Institute's repository in Moscow. A transfer form exists. The core from the anomalous horizon was labeled and stored in a refrigerated unit designated for organic-bearing sediments. A 1978 inventory of the same repository lists the unit as decommissioned due to cooling failure. Whether the core was relocated or lost is not recorded. But the evaporite horizon exists in the published data, thin as a fingernail and older than any map. What it means is that the Aral has died before completely, without warning in the geological sense, and refilled and died again. The prehistoric version of the sea did not disappear because of irrigation. It disappeared because it was always capable of disappearing. The sulfur smell that Petrov broke open with his thumb was the exhaled breath of a lake that had already rehearsed its own absence. More than once. The thermal layers. The ancient Aral Sea had a thermal structure that the modern lake never developed, and what lived in the cold at the bottom was not incidental. A limnologist from the Leningrad Hydrometeorology Institute was conducting vertical temperature profiling in the deepest surveyed zone of the Aral in 1955. Lowering a calibrated thermistor chain on a weighted cable from the side of a research vessel. At 30 meters, the temperature dropped by 6 degrees in less than 2 meters of depth, a thermocline sharp enough that the instrument's reading when it came back up to the chart recorder drew a near-vertical line on the paper. The technician operating the recorder put his finger on the line without touching it, as if to confirm it was ink and not a malfunction. Dr. Igor Krasnov, physical limnologist at the Institute and the study's principal investigator, had profiled thermal structure in Lake Baikal and several Siberian reservoirs, and described the Aral's thermocline in his field log as unexpectedly pronounced for a closed basin of its surface area. Below the thermocline, the water temperature held at just above 4 degrees Celsius, cold enough that Krasnov noted in his personal journal that the deep water behaved as if it had been there for a long time without disturbance. He did not elaborate. The phrase appears once, then the journal continues with instrument calibration notes. The Institute's published report described the thermocline as a seasonal feature consistent with continental climate patterns. The cold, deep layer was noted in the data tables. The description of the layer's stability, its apparent age, its resistance to mixing, did not appear in the official summary's interpretive sections. The thermal profile data was incorporated into a broader limnological atlas of Soviet inland waters published in 1959. The Aral entry runs to 4 pages. The thermocline figure is reproduced. The accompanying text characterizes the deep layer as typical. A cartographer's note in the atlas margin visible in archival scans reads, "Verify depth scale. It is not clear that anyone did." And yet the cold layer below the Aral's thermocline, extrapolated to the prehistoric basin's depth, would have been a permanent feature, stable across seasons, across decades, across centuries. In that kind of cold, biological time slows, things that sink into it are preserved. Things adapted to it are adapted to a kind of patience that nothing in the warm upper water can develop. If you descended through that thermocline without preparation, the cold would register first in your hands, then in your chest, then as a pressure behind your eyes that no amount of equalization corrects. You would feel the boundary before you saw it. The lake kept its own counsel below that line. The paleofauna, what lived in the deep Aral before the historical record, is not entirely unknown, and some of it is not small. In 1971, a construction crew excavating a drainage channel near the former southern shore of the Aral Sea struck bone at a depth of approximately 3 meters below the current surface. The site foreman stopped the machinery and sent a man on foot to the nearest phone to call the regional museum in Nukus. A paleontologist arrived the following morning with a field kit in a canvas bag, knelt in the mud of the drainage trench, and began brushing around the exposed material with a stiff-bristled brush, working slowly enough that by afternoon she had exposed the articulated vertebrae of something large enough that the construction crew, watching from the edge of the trench, began discussing what it was among themselves without reaching agreement. Dr. Nelia Ibrahimova, vertebrate paleontologist attached to the Karakalpak Regional Museum System, identified the material as belonging to a large aquatic reptile consistent with Cretaceous-era fauna, a body plan suited to deep, open water and likely capable of sustained diving. The specimen's size, estimated from the exposed vertebral column, suggested an animal in the range of 4 to 5 meters in length. Ibrahimova photographed every exposed surface before allowing further excavation. She sent the photographs to the Institute of Paleontology in Moscow by registered mail the following week. Regional press reported the discovery as an interesting fossil find, evidence of the area's ancient sea history. The Moscow Institute's acknowledgement of Ibrahimova's photographs is not in the public record. A note in the Nukus Museum's accession log from 1972 records partial fossil material received from the drainage site and catalogued under regional Mesozoic fauna. The full specimen, if it was excavated, does not appear in the accession log. The Institute of Paleontology published a survey of Central Asian Cretaceous vertebrates in 1974. The Nukus drainage site does not appear in its site index. Ibrahimova's name appears in one footnote, crediting a personal communication on regional stratigraphy. The footnote does not mention the photographs. But the drainage trench coordinates place the find site in what would have been, during the Cretaceous, the open central basin of a fully marine tethys-connected sea, warm, deep, and continuous with oceans that no longer exist in the same configuration. Whatever Ibrahimova's brush uncovered had been down in that water for reasons the water no longer has. 4 to 5 meters of animal built for depth and distance, lying 3 meters below a field that a construction crew was turning into an irrigation ditch. The gap between those two facts is not a metaphor, it is a measurement. The winds after the water left, when the Aral began to dry, it did not simply shrink, it became a machine. A public health officer in the Aralsk district filed a report in 1978 noting an increase in respiratory clinic visits during high wind periods. She had been tracking the pattern for 2 years by the time she submitted the report, correlating clinic intake dates with wind speed and direction records from the regional meteorological station. She submitted the report to the Oblast Health Authority and received a reply acknowledging receipt. She kept a copy in a filed drawer in her office. She did not stop tracking the correlation. Dr. Philip Micklin, a geographer at Western Michigan University who became one of the primary English-language documentarians of the Aral's collapse, later described the exposed lakebed as one of the most significant sources of salt and dust aerosol on the Asian continent. The dried sediment, saturated with agricultural pesticides and chemical residue from decades of cotton irrigation runoff, became airborne in the regional winds and was deposited across a corridor extending hundreds of kilometers from the former shoreline. Micklin noted in a 1988 paper that the dust had been detected in blood samples taken from children in communities downwind, not in general population surveys, in children. Soviet health authorities described elevated respiratory illness in the Aral region as consistent with regional climate conditions and ongoing study. A 1980 health report for the Karakalpak Autonomous Region noted increased incidence of throat and lung ailments. The causal framing in the report described environmental factors generically. The word dust appeared once, The word pesticide did not appear. 1985 internal Soviet environmental review of the Aral region was completed and submitted to the State Committee for Science and Technology. The review was classified. A summary of the summary was made available to regional health administrators in 1987. The full review has not been fully declassified. A ministry official was photographed at a press briefing in 1986 describing the Aral situation as a matter of ongoing management. The briefing ended after 20 minutes. No follow-up briefing was scheduled. And yet the dust record is not confined to Soviet files. It settled, it was inhaled, it entered the cellular material of people who lived in a region that used to be downwind of nothing but open water, and what it carried with it, the chemical residue of a collapsed agricultural system layered over the mineral bed of a prehistoric ocean, does not appear on any map as a single event. It appears in X-rays, it appears in spirometry readings. It appears in the way a chest sounds when a doctor puts a stethoscope against it in a clinic in a city that used to be a fishing port and is now 60 kilometers from the nearest water. The villages that watched it go, the communities at the Aral's edge did not lose a lake, they lost the architecture of survival. A fisherman in the village of Uyali, on the northern Kazakh shore, was repairing a net in the summer of 1971 when he noticed that the reed beds at the waterline were standing on exposed mud that he did not recognize as the shoreline. He had grown up on that shore. He walked out to where the water should have begun and kept walking before his boots touched water. He stood there for a moment, then walked back and finished the net. He did not record this in any document. It was noted later in an oral history collected by a Kazakh ethnographer in the 1990s. Dr. Salesh Esenova, a sociologist at the University of Manitoba who conducted fieldwork on Aral region community displacement, documented in a 2003 study that fishing villages along the former northern shore experienced complete economic collapse within a single generational span, fathers who had worked the water and sons who could not find it. Communities had no institutional mechanism for the kind of change that happened, Esenova noted, because the change was not the kind of thing that institutions were built to address. It was the permanent disappearance of the physical basis for a way of life. She recorded one interview subject who described learning to fish from his father and teaching his own son to fix trucks. He described it without apparent emotion. That absence, Esenova noted in her field journal, was its own kind of data. Soviet agricultural and planning documents from the 1960s and 1970s described the water diversion from the Amudarya and Sirdarya rivers as a strategic development of regional productive capacity. The Aral Sea's reduction was acknowledged in internal planning documents as a projected outcome. The phrase used in one 1968 planning document, cited in subsequent analyses of the period, was an acceptable sacrifice for agricultural development. The communities near the shore were not consulted. The document does not record whether they were considered. A Soviet Environmental Planning Commission convened in 1974 to assess the Aral's status, concluded that remediation was technically possible but economically impractical at current projections. The commission's report was filed with the State Planning Committee. A commissioner signed the final page. The plan for remediation was not initiated. The shrinkage continued at the rate that the diversion engineering had made inevitable. But no planning document describes what it looks like when a shoreline retreats past the boats. The boats at Uyali and Minek and Aralsk sat in the mud, and the mud dried and the wind came and the boats stayed where they were, tilting slightly each season, and the men who had crewed them found other work or didn't, and the water moved away from the village at a pace that was too slow to see in a day and too fast to survive across a decade. If you stood on the bow of one of those grounded boats and looked toward where the water was, you could see it, a faint shimmer at the horizon, receding. Not a metaphor, just the view. The version that is coming back. The northern Aral Sea is refilling, and the question no one is asking is what it is refilling into. In 2005, Kazakhstani engineers completed construction of the Kokoral Dam, a concrete and earthwork structure built across the Berg Strait that separates the northern and southern basins of what remains of the Aral Sea. The lead engineer on the project was photographed at the ribbon cutting holding a pair of scissors he did not immediately use, looking at the water behind the new structure for a moment before cutting. The water behind the dam had already risen 14 centimeters from the previous week's level. He cut the ribbon. The cameras recorded it. The water kept rising. Dr. Nikolai Aladin, a hydrobiologist at the Zoological Institute of the Russian Academy of Sciences in St. Petersburg who had monitored Aral biota through the collapse, conducted surveys of the small Aral's recovering fish population in 2006 and 2007. He recorded the return of flounder, bream, and pike perch to waters where they had been absent for 2 decades. He also recorded in his field notes the return of invertebrate species whose presence suggested the sediment layer below the recovering water column was reactivating, releasing stored organic material back into the water cycle. He described the water in a recorded interview as smelling in certain zones like something old. He did not use another word for it. The Cockerel Dam project was reported internationally as an environmental success story: a lake saved, a fishery recovered, a community restored. The Kazakhstani government issued statements describing the Northern Aral's recovery as proof of the viability of managed ecological restoration. United Nations environmental agencies cited the project in subsequent publications on inland water management. The southern basin, which received no dam and no remediation funding, continued to dry. It is now, in most of its extent, a salt flat. The World Bank, which co-funded the Cockerel project, published an evaluation in 2010 describing the restoration as meeting its primary benchmarks. Water volume, salinity, and fish catch figures were cited. The evaluation noted remaining challenges in the southern basin. A section on long-term sustainability described the dam as requiring ongoing maintenance investment. The section did not describe what the sediment reactivation Aladdin had noted might mean for water chemistry over the next century. But the water rising behind the Cockerel Dam is not filling an empty basin. It is filling a basin layered with a century of pesticide residue, 2 millennia of sediment compressed by a lake that no longer existed, and below that, the mineral bed of a Pleistocene sea whose salinity and depth and thermal structure bear no relationship to the fishery the engineers are trying to restore. The flounder coming back are coming back to something that is wearing the Aral Sea's address, but not its history. And the sediment waking up below them, releasing what it stored when the water left, is doing so at a pace too slow to see in a season and too certain to stop. What is returning to the surface of that recovering lake, molecule by molecule, is everything the lake has ever been, and some of it was never safe for anything that breathed air and stood upright and thought it was just standing at the edge of the water. Every lake in this story disappeared the same way, officially, gradually, and then all at once. The Aral Sea's timeline is a document with the same ending written in different centuries, and the version being written now is the one where we added the chemicals first. If you want to see more videos like this, click the video on screen now and make sure to subscribe. If you want more videos like this, subscribe.